Hello, my people. Good morning, good afternoon, good evening. This is Tasien. I am happy to be here again. Welcome to Mathify Analytics. We are happy to have you here. Welcome. In today's video, I'm going to solve this question. It's a differential equation and you can see it on the screen. And it was part of the national examination that was done in Rwanda for grade 2 students who were in these sections, the following sections. Yeah, there were students in the MCB, MCE, MEG, and PCM, and the MPG. So I hope many students are waiting to see how we can solve this differential equation, and in this video I'm going to solve it for you. I hope you are going to like my solution. If you don't like the solution, let me know, and if you like the solution, just click like and share the solution to your friends. Yes, so the question was to find a general solution to this differential equation. This is a second order linear differential equation, and normally the general solution of this kind of differential equation is of the form y equal to yh plus yp. And what is yh and what is yp? YH is an homogeneous solution, and this homogeneous solution YH is obtained by solving this differential equation when this second hand part is equal to 0. So the YH is obtained by solving the differential equation y second derivative minus 2 y derivative plus y equal to 0. And the particular solution, there is a different way to find the particular solution based on this right hand side of our differential equation. Yes, so let's start by finding the homogeneous solution yh. So we are going to solve this differential equation. And to solve this differential equation, we have to solve first this characteristic equation of this differential equation. The characteristic equation will be of the form r squared minus 2r and then plus 1 equal to 0. Because we have 1 here and we have minus 2 and 1 here. So these are those coefficients that I'm using. And we have that, sorry, taking everything off, so but I'm going to write it again. Sorry, we had here y second derivative minus 2 y derivative plus y equal to 0. Yes, so this characteristic equation, you can see that this can be written as r minus 1 squared. This is from the fact that I think you remember that a plus b squared is equal to a squared plus 2ab and plus b squared. What about a minus b squared? And a minus b squared is equal to a squared minus 2ab and plus b squared. So we are using this second one, and then we have this r minus 1 squared. So we have r minus 1 squared equal to 0, and you can see that we have r1 equal to r2 and is equal to 0. Here we have double solution, double root. Since we have double root, in this case our differential equation homogeneous solution will be of the form yh will be of the form a plus b x and times e power r1 x, and r1 is equal to r2 and is equal to 1. So there we will have 1. Okay, so then we have e power e power x, because our root is equal to 1. So this is the homogeneous solution. So next, what do we have to do? We have to find this particular solution yp, and to find this particular solution, it will depends on what we have here, this function here. Since we have this function, the function of this form, we cannot use the indeterminate coefficient method, but we can use the variation of parameters method. So if we use the variation of parameters method, I suppose that you know those methods, different methods. But hey, write in the comment section if you don't know all those methods, or if you want me to make a reason on the differential equation, just to show you different ways to solve differential equations. Write in the comment section and let me know. So we are going to use here variation of parameters methods. If we use the variation of parameters method, what are we going to do? We are going to suppose that our particular solution yp will be equal to u1 times y1 and plus u2 times y2. Yes, where y1, what is y1, and what is y2, what is u1, and what is u2. Here y1 will be equal to the first solution obtained by using r1, which is e power x, and the other one will be y2 will be equal to x e power x. Yes, so it's the solutions that we have in this homogeneous solution. So y1 equal to e power x for r1 equal to 1, then r2 also equal to 1. So we have this y1 and this y2, and what is u1 and what is u2? That's what we are supposed to find. And how do we find u1 and u2? We have to find what we call Wronskian, the Wronskian of our differential equation, the Wronskian W. Let me call it W. Let's take this one a little bit up. I take this a little bit up. Sorry, I want to take this a little bit up. All right. Yes. We compute the Wronskian, I call it W. The Wronskian is equal to the determinant of y1, y2, and y1 derivative and y2 derivative. So we have to first compute y1 derivative. We have y1 equal to this one. This implies that y1 derivative is equal to e power x derivative, and this is equal to e power x. And y2 derivative is equal to x times e power x derivative. We have y2 here. So y2 derivative is the derivative of it, and it is equal to e power x and plus x e power x. And then what will be the Wronskian? Then you can see that this Wronskian W will be equal to y1 is e power x and y2 is x e power x, and y1 derivative is e power x, y2 derivative is e power x, and plus x e power x, and we compute the derivative, the determinant, not the derivative. So this determinant will be equal to what? Let's take this one a little bit up again. Yeah, this determinant will be equal to what? Yes, this our w becomes what? It will become e power x times, we take this multiplied by this and this and this. So e power x times e power x plus x e power x and minus e power x times x e power x. So this was w equal, so we have our w equal to e power 2x plus x e power 2x minus x e power 2x, and you can see that these and these are simplified and we get our Wronskian to be equal to e power 2x. Since the Wronskian is equal to e power 2x, now we are able to compute our parameters u1 and u2. So how do we compute parameters u1 and u2? How do we compute these two parameters? How do we compute these two parameters? To compute u1 is always equal to minus y2 times f of x. And what is f of x? F of x is the right hand side of our differential equation and over Wronskian, and this is the derivative of u1, and the derivative of u2 is equal to y1 times f times f of x over Wronskian. So from here we will get that u1 derivative is equal to minus y2 is x e power x, and our function, the right hand side of our differential equation was, let's see, it was e power x over x squared plus over x squared plus 1. So we have here e power x over x squared plus 1, and then over the Wronskian, and the Wronskian is e power 2x. This is the first derivative of u, so this will be equal to what? So you can see that on the numerator we have minus x e power 2x, then over this will be over x squared plus 1 and times e power 2x. So this one and this one will be simplified, and we will remain with u1 derivative equal to what? We remain with u1 derivative equal to minus x over x squared plus 1. Yeah, so then since we have the derivative, we can compute. So this implies that u1 will be equal to the integration of u1 derivative dx. So this will be equal to integration of minus x over x squared plus 1 dx. And you can see that this is the same as minus integration of x over x squared plus 1 and dx. And you can see that this is equal to what? This implies that u1 is equal to, we integrate this is minus ln of absolute value of x squared plus 1 over 2, because when we differentiate x squared plus 1, we should have had 2 here, but since 2 is not there, so we have to divide it here. All right, so this is u1, and what is u2? To compute u2, we have to first compute u2 derivative, and u2 derivative, as I have just said, it's that u2 derivative is given by this relationship So u2 derivative will be equal to what? We will have u2 derivative equal to y1, and y1 is e power x, and f of x is e power x over x squared plus 1, and then over Wronskian. The Wronskian is, we have found that it is e power 2x. Alright. And then this is equal to what? This is equal to e power 2x, yes, over x squared plus 1 times e power 2x. So e power 2x and e power 2x are simplified, and we remain with 1 over x squared plus 1. Yes, this is the derivative of our parameter u2. So this implies that u2 will be equal to integration of u2 derivative dx. So this is equal to integration of 1 over x squared plus 1 dx, which is equal to tan minus 1. This is inverse tan of x. So we have u1. Let me take another color. Alright, we have u1 equal to this. This is u1. Yes. And we have u2 equal to this. Let me write it down here. Let's take this a little bit up. Yes. We have u2 equal to tan minus 1 of x. Yes. And therefore, our particular solution yp, which was equal to u1 y1 plus u2 y2, will be what? We will have, I take a black color better. So we will have yp equal to u1 is minus 1 over 2 ln of x squared plus 1 absolute value, then times y1, and y1 was e power x, and then plus u2 is up there. This is tan minus 1 of x, and then times y2, and y2 was x e power x. Okay, all right. And then yp will be equal to what? This is the same as writing minus 1 over 2 e power x ln of absolute value of x squared plus 1 and plus x e power x times tan minus 1 of x. Or we can also say that it is equal to what? This is the same as, let me use another color. This is the same as yp equal to e power x and times minus 1 over 2 ln of x squared plus 1 absolute value, of course, plus x tan minus 1 of x. Yes, this is the particular solution. And then the general solution of our differential equation, will be equal to the homogeneous solution plus the particular solution. The general solution of our differential equation is it will be y equal to yh, homogeneous solution, plus yp. and which is y equal to, and do you remember the homogeneous solution that you have obtained? This was a plus b x e power x. Then we add our particular solution, the particular solution, which is e power x times minus 1 over 2 ln of x squared plus 1 and plus x times tan minus 1 of x. Yes, so that's it. This is our general solution. This is the general solution that we are asked to compute. So that was it, and thank you for watching. I hope you have learned something from this equation, and you will be able to solve a similar solution if you happen to be asked to solve a differential equation of this kind. I hope you like the video. If you like it, just click like and share the video to your friends. Tell them that we are here to help. And if you have any question, write it in the comment section and let us know. Let's discuss. Alright, thank you for watching, and I hope to see you for the next question. Next question will be question number 18, and hope to see you again. Bye. Thank you for watching.